Let me ask you something strange. Right now, as you sit or stand watching this, do you feel the earth pulling you down? Of course you do. You feel weight. You feel the ground beneath you. But what if I told you that what you're feeling right now is not gravity at all? What if I told you that you right now are not standing still but constantly falling? And what if I told you that gravity, the force we've believed in for centuries, the force that Isaac Newton described so brilliantly, doesn't actually exist the way we thought it did? I know how that sounds. It sounds impossible, but I spent years of my life thinking about this exact question, and what I discovered changed everything we thought we knew about the universe. I discovered that gravity is not a force pulling you down. Gravity is something far stranger, far more beautiful. It is the shape of space and time itself, and once you understand this, you will never see the world the same way again. My name is Albert Einstein, and today I want to take you on a journey. Not a journey through space, but a journey through thought. I want to show you how I came to realize that the universe works in a way no one had imagined before, and I promise you by the end of this, you will understand something profound about reality itself. Let me begin with a simple question that haunted me for years. Imagine you are standing in an elevator. The elevator is closed, so you cannot see outside. You feel your normal weight pressing down on the floor. Now tell me, can you tell the difference between standing in that elevator on Earth and standing in that same elevator out in deep space? Far from any planet while the elevator is being pulled upward with a constant acceleration. Think carefully. In both cases, you feel weight. In both cases, your feet press against the floor. In both cases, if you drop a ball, it falls to the floor at the same speed. So how can you tell which situation you are in? Let me show. Imagine you are in that elevator again, but this time the cable holding it snaps. The elevator begins to fall. What happens to you? You start floating. If you were holding a ball and you let go, the ball doesn't fall to the floor. It hovers next to you. You and everything inside the elevator are falling together at exactly the same rate. Inside that falling elevator, you feel no gravity at all. You feel weightless, just as if you were floating in deep space, far from any planet or star. Now here is the strange part. While you are falling, while the elevator is plummeting toward the ground, you feel no force. You feel completely free, but someone standing on the ground watching you would say you are accelerating downward, pulled by the force of gravity. So which is it? Are you being pulled by a force, or are you simply moving freely through space? I realize that you inside the falling elevator are actually correct. You are not feeling any force. You are moving freely, and this is the key insight. What we call gravity is not a force pulling on you at all. When you are falling, you are following the most natural, most free path through space and time. It is only when something stops your fall, when the ground or a floor pushes up against you, that you feel a force. That force you feel when you stand on the ground, the force you call your weight, is not gravity pulling you down. It is the ground pushing you up, stopping you from following your natural free fall path. This was a radical idea. For centuries, ever since Isaac Newton, we believed that gravity was a force, an invisible pull between objects with mass. Newton's laws worked beautifully. They explained the orbits of planets, the tides of the oceans, the fall of an apple from a tree, but Newton himself admitted that he did not know how gravity worked. He could describe its effects mathematically, but he could not explain what it truly was or how it reached across empty space to pull objects together. I wanted to understand the mechanism. I wanted to know what gravity really was, and the equivalence principle gave me the answer. If falling is the same as moving freely through space, and if standing still on the ground means experiencing an upward force, then gravity must be something about the structure of space and time itself. Objects are not being pulled. They are simply following the natural shape of the universe. but how can space have a shape? We are used to thinking of space as empty, as nothing. We imagine space as a stage on which events happen, but not as something that can bend or curve. Yet I realize that space and time as well must be more than just an empty stage. Space and time must be like a fabric, something that can stretch and curve and warp. Imagine a trampoline stretched flat. If you place a heavy ball in the center, the trampoline sags. It curves downward around the ball. Now, if you roll a smaller ball across the trampoline, it will not travel in a straight line. It will curve toward the heavy ball, following the curved shape of the trampoline's surface. The smaller ball is not being pulled by the heavy ball. It is simply following the natural curved path created by the shape of the surface itself. This is how gravity works. Massive objects like the Earth, the Sun, or a star do not pull on other objects. Instead, they curve the fabric of space and time around them, and other objects like you or the moon or a planet simply follow the curved paths through this shaped space. What we call the force of gravity is actually just the natural motion of objects through curved spacetime. When you stand on the Earth, you are not being pulled down. The Earth has curved spacetime around it, and your natural free fall path is to move toward the center of the Earth, but the ground is in the way. The ground pushes up on you, stopping you from following that free fall path. That upward push is what you feel as your weight. It is not gravity pushing you down, it is the ground pushing you up, preventing you from falling. And when you are in an airplane or in orbit around the Earth, you are not defying gravity. You are simply following your natural path through curved spacetime. Astronauts in the International Space Station feel weightless not because there is no gravity up there. In fact, the Earth's gravitational pull is almost as strong at that altitude as it is on the surface. They feel weightless because they are in free fall, following their natural curved path through spacetime, falling around the Earth, rather than straight down into it. This is the heart of my general theory of relativity. Gravity is not a force. It is the curvature of spacetime caused by mass and energy. And everything in the universe, from the smallest particle to the largest galaxy, follows the curved paths through this spacetime. What Newton called a force pulling objects together, I described as the geometry of the universe itself. Now you might ask, how do we know this is true? After all, it sounds like a strange, almost magical idea, but the universe itself gave us the proof. I predicted that if space-time truly curves around massive objects, then even light, which has no mass, should follow those curves. When light from a distant star passes near the sun, its path should bend. The star should appear to shift its position slightly in the sky. In 1919, during a total solar eclipse, astronomers measured the positions of stars near the sun, and they found exactly what I predicted. The light from those stars had indeed bent as it passed near the sun. The curvature of spacetime was real. Gravity was not a force, it was geometry. This discovery changed everything. It meant that space and time were not separate, fixed things. They were dynamic, flexible, woven together into a single fabric that could stretch and bend and ripple. It meant that massive objects do not just sit in space, they shape the very space around them. It meant that the universe itself has a geometry, a structure that can be studied and understood. And this understanding opened up entirely new ways of thinking about the cosmos. It explained why the orbit of Mercury was slightly off from Newton's predictions. It predicted the existence of black holes, regions of spacetime so curved that not even light can escape. It suggested that the universe itself might be expanding, growing larger over time, and it laid the foundation for everything we have learned about the universe since. But perhaps the most beautiful part of this discovery is how simple the core idea is. You do not need complicated mathematics to grasp the essential truth. You only need to imagine what it feels like to fall, to float freely, to move without any force acting on you. That feeling of weightlessness, that sense of freedom, is not the absence of gravity. It is gravity itself. It is you following the natural shape of space-time. When I first realized this, I felt a sense of wonder that I have rarely experienced in my life. I had spent years thinking about these problems, wrestling with contradictions, trying to understand how the universe could work, and suddenly it all made sense. The pieces fit together. The universe revealed itself not as a collection of forces pulling and pushing, but as a beautiful geometric structure, elegant and profound. And here is what I want you to take away from this. The next time you stand on the ground, the next time you feel your weight, remember that what you are feeling is not gravity pulling you down. It is the earth, massive and solid, curving space-time around it, and the ground beneath your feet pushing you up, stopping you from following your natural free fall path through that curved space. You are not standing still. You are being accelerated upward, away from the shape the universe wants you to follow. And the next time you see an astronaut floating in space, remember that they are not defying gravity. They are embracing it. They are following the most natural path through curved space-time, falling endlessly around the Earth, free and weightless, experiencing what gravity truly is. This is the universe we live in, a universe where space and time are not empty backdrops, but active participants in every motion, every orbit, every fall. A universe where what we call forces are often just the shapes and curves of reality itself. A universe far stranger, far more beautiful than we ever imagined. And the most remarkable thing is that we can understand it. We can use our minds, our imagination, our careful reasoning to uncover the deep truths about how reality works. We do not need to accept things as they appear. We can question, we can think, we can discover. That is the greatest gift of science, not just the facts we learn, but the sense of wonder we feel when we realize that the universe is comprehensible, that its mysteries can be solved, that beneath the surface of everyday experience lies a profound and elegant order. So keep asking questions, keep wondering why, keep imagining what the universe might truly be like beneath its surface, because that curiosity, that desire to understand, is what allows us to see reality as it truly is. And reality, I promise you, is far more fascinating than any fiction we could invent.